promise to bring them by 7:30, so be there. Okay. All right, so then we'll start the second lecture. So Professor Batyrev will continue with cohomology, theory, and so on.
Okay, so today I would like to speak on some other combinatorial invariants of which appear in the connection to periods and Hodge structure, etc. So we start with the lattice polytope, and we consider some formal power series P delta T, just the sum over all. Okay, great. I will write down T to the power. Okay, so I denote by L of K delta just the number of lattice points in the K multiple of delta. So you can interpret also this power series as Poincare series of graded rings. So you have the graded ring, and one knows that the homogeneous components of each graded ring of this graded ring have a monomial basis, and they can be chosen as lattice points in K multiple. So you can write down this form. And the dimension of each component is exactly L of K delta. So, and by general statement from commutative algebra, one knows that such a power series, which counts the dimension of homogeneous components of finitely generated graded algebra, is a rational function. But for this special kind of graded finitely generated algebra, this is monomial algebra of generated by monomials, we have much more information. So it turns out that the power series can be written in as a rational function in the following form: 1 t plus 1, and here it will be some polynomial psi of delta t. And the degree of this polynomial psi of delta t is not greater than d. Maybe just for illustration, in order to see how it works, we can consider an example again. Let's take even one-dimensional example. So delta will be just like our interval, so it's delta. So then you can write down what is the number of lattice point in K multiple of delta. Delta. It will be exactly Kn plus 1. And now you can write down this power series. The power series will be just a summation of K over Kn plus 1 to the power K. You can summate it in a very easy way. It will be this one gives a geometric series, and the same this will be some kind of still be n 1 t squared. So you'll get actually rational function with denominator here squared, and here you'll get 1 plus n minus 1 t. So this is degree of this is so d in this case is d is 1. So this is how you will get an example. Well, what is also interesting? Questions? N minus 1 times t. No? Something wrong? Sorry? 1 plus n minus t, yes?
Without the parentheses.
Coefficient of t is 1.
Coefficient of t is 1? Oh, sorry. Sorry. Then maybe I'm wrong in the computation. Sorry. No. Sorry. Yeah, maybe I'm wrong. The second series. This is the correct answer, but maybe not correct computation. So this, I'm sure about this. I'm not sure, but it's the answer. Remember, because if you just take the second will be. So I forgot T. No, sorry. This is sorry. This was a mismatch. Sorry. So just shift. Well, you can do similar exercise for another function. Let me take another sheet of paper. So we write down another power series denoted by Q delta. This is a summation of all non-positive K, and we consider just number of interior lattice points. Okay, so it's again this will be integer number of we take interior of the K delta and intersect it with. And again, you'll get a rational function. So this power series, in fact, is a rational function. You can write down this function again in the form d plus 1. And here you get another polynomial. This polynomial, degree of this second polynomial, will be exactly d plus 1 because it will be a top coefficient 1. Again, maybe just as an example, if you take this integral, then the power series you need to summate will be a summation of nk here will be minus 1. But let me tell you the answer, another computation, because what it's easy, it's the same. So it will be 1 minus t squared, and here you'll get, in the polynomial, will be t squared plus n minus 1t. So that means the degree will be the same of the numerator and denominator will be the same. So what is important, if we compare two polynomials, phi delta of t and psi delta of t, so it was first and this was second, just appeared here, then one can see that there is some duality between coefficients. This duality can be formulated as follows. The second polynomial can be written as t to the power d plus 1 and psi to the power t minus 1. So that means, in other words, so this duality is called another formulation, Ehrhart reciprocity law. Maybe just to write down in coefficients, what does it mean? So the polynomial, yes. Yeah. So maybe I write down here. So if we write down one polynomial just as sum of phi I delta t and psi delta just psi j, Yes, then dual. First of all, what is not obvious, but it can be proved also. In addition, that you get a function in the rational function of precise form, all coefficients are non-zero, non-negative, and they satisfy the following condition. So psi I of delta is equal to phi d plus 1 minus I delta for all I. In this situation, you need I in between 0 and d. Well, it's obvious that psi 0 of delta is 1 because, well, this, the counting points of now lattice points starts with 1. The homogeneous degree 0 has dimension 1. What is less obvious is that, but it follows from the duality. Here maybe I should write. So phi of delta is a number of interior points of in delta, but by duality, this number is nothing but psi of delta. So this number turns out to these two numbers, and of course this is again this is phi d plus 1 of delta. So this is 1. So we have this duality. And it turns out that this duality between numbers, which can be proved, and in my notes I gave also a proof, because and the proof actually reduce to the case. First, you consider the case of simplex. For simplex, you can write down somehow something explicit way, and then you take a triangulation of arbitrary lattice polytope in simplices, and then apply result for simplices to each element of triangulation. But behind this combinatorial duality, there is a duality from commutative algebra. Actually, as you probably remember, there is a graded Artinian ring, which we constructed from Laurent polynomial. We constructed regular sequence and divided by ideal generated by this regular sequence our graded ring, and it will be its Artinian ring. And it just, if you look at resolution of this Artinian ring Kazul complex, and you can immediately see that computation of the generating function for dimension of homogeneous component of this Artinian ring is actually the same as a computation of polynomial psi. So that means if you take just a Poincare series of this ring, you get exactly polynomial psi of that. That means dimension of each component of this homogeneous of this graded Artinian ring will be exactly psi I of delta. But no, it's not only one object which is what is interesting in this connection. There is another object which is a module over this ring. It's constructed as follows. First, we constructed an ideal in the ring as delta. This ideal generated by all interior points. It's spanned by all interior points in the cone over the delta intersecting with a lattice. So it's linear span. So the basis for the as vector space for the ring S delta is just monomials in the cone. All monomials in the cone over delta, but here we have monomials just in the interior of the cone over delta. So it's obviously it's an ideal, and it's actually it's a canonical ideal, but I don't want to make precise definition what it is. So there are some references in commutative algebra, Grothendieck duality theorem, so where it's used. Oh, the most important is you can apply the same procedure as you did for a ring S delta to this ideal. So you can take consider as a module and divide by a regular sequence. And what you will get, it will be module, so I will denote it by IF. It will be a module over this graded module over this graded ring. And one can show that the second function that I mentioned today, so that this power series curve delta, it's exactly generating function for the dimensional homogeneous component associated with this ideal. So it counts homogeneous components of this ideal. Moreover, this polynomial phi of delta, or what was just product of this Q delta, it's nothing but the counting function, so generating function for dimension of homogeneous component of this finite dimensional module. So this is a finite dimensional module, and dimension of homogeneous component k will be exactly phi k of delta, so coefficient of this polynomial. Moreover, what I wanted to say, we have a ring f. We have also a module over this ring, and we have natural multiplication, module times just structure multiplication. It's a graded, so both are graded, so you can take a homogeneous pieces, and you get the following. So you, if you multiply with homogeneous piece of degree d plus 1 minus I, you will be in this homogeneous degree, but this is canonically isomorphic to base field. So you can find canonical isomorphism of this last non-zero. It corresponds exactly to the last coefficient in this top coefficient one in this polynomial phi. As I said, it will be of degree d plus 1, and it will be the last maximal non-zero degree component. And so we have a perfect duality. So there is an isomorphism between this as vector space and the dual to this. So these are important combinatorial duality, and not only combinatorial. As I said, there is a duality between vector spaces, and already these vector spaces, they depend on the choice of polynomial f. So we have some more structure.
Excuse me, sir.
Yes.
I got a bit confused, but this is for any polynomial which satisfies this regularity condition?
Yeah, if polynomial f satisfy regularity condition, then we have a regular sequence, and we have this Artinian ring. So, but of course, if we vary coefficients, the dimensions do not change. So it will be somehow deformation. So we can say that we can deformate multiplication in this ring. So the rings that you get if you deform coefficients of polynomial f will be not necessarily isomorphic to each other. But if you look only at dimensions, so vector spaces, you get the same answer.
Yeah, but I mean, this ring theoretic duality depends on the regularity condition.
Not complete. So it's also so this in form that I formulated. It depends, but one can consider much more general version. So in our situation, we have duality. So one can generalize. So I believe that there is also some kind of objects, explicitly computed objects corresponding to non necessary this delta.
I think there's a combinatorial description of the dualizing complex.
Yes, the dualizing complex. Yeah. But well, I don't want to go to the direction. Yes. Here we don't have complex, we have only module. So now I would like to explain how these rings and ideals appear in connection to cohomology. Sorry, cohomology. So cohomology of I'm interested in cohomology of hypersurface, and so we have a torus. We have a equation. So we have a hypersurface in d-dimensional torus, and we want to understand this cohomology. So it turns out this understanding related to the previous. So we can I would like also to say our hypersurface is affine, not compact. For this, but it's smooth. And for this reason, it's more natural to consider not only cohomology, usual cohomology, but also cohomology with compact supports. Cohomology with compact supports are necessary if you would like, for example, to apply some cohomological formula like number of fixed points using trace of action in cohomology. So for compact, it's okay, but if you are working with non-compact variety, you don't have that result that number of fixed points is exactly the alternating trace of action in cohomology, but you should consider work action in cohomology with compact supports. And in our situation, the relation between cohomology and cohomology with compact support is the following. So there is so the cohomology, so our variety is we can assume that D is at least 2, because if D is 1, we have only finitely many points. It's not so interesting. But for D, at least 2, we have connected variety, and that means that the H0 will be always Z if you compute it. But this fact, if you go to cohomology with compact support, it implies that the top cohomology of the hypersurface, so let me write down, we have D minus 1 twice of because compact support of this. So we consider as a hypersurface of a complex number. I forgot to say. Now I'm interested in hypersurface in the torus, but over C. So that means it's isomorphic to C star to the power D minus 1. So, and then the real dimension of this hypersurface will be twice D minus 1, and also isomorphic to Z. So it's, and in fact there is a duality between HI, so cohomology, usual cohomology, and cohomology with compact support but complementary. So we have minus I. So this maps to HD minus 1, of course isomorphic to Z, and it was not a coincidence that I have written in this form. It should remind you, then later you will see previous duality that we have for some Artinian ring and canonical and some module over this Artinian ring. I mean this duality between SF to this. Well, so. Let's return back to our hypersurface. So we have a hypersurface in the torus, and first result. So first topological characteristic that we can ask about this hypersurface would be probably the best and easier Euler number. So we can write down. So we can take alternating sum over I minus I dimension of HI. So the Euler number, and we can compute it. So there is a result due to Hovansky and Danilov. First simplest result, which express this Euler number using some combinatorics. Namely, this Euler number is nothing but minus 1 to the power D minus 1 times volume of normalized volume of the polytope delta. So this is a first connection between cohomology and combinatorics. I would like also to remind you that this number is factorial times usual volume of delta. So, but this is always in a negative integer. And also, I would like to remind, in order to keep connection to our previous, the dimension of this Artin ring, and will be the same as dimension as of this module. They have the same dimension. It's also volume of delta. Well, of course, maybe you think that these are exactly rings that describe cohomology, but it's not quite correct. So there are some. It's almost correct, but not quite. I would like to explain you. So, of course, the same number appear here as another. Let me explain roughly how the cohomology looks like and how it can be computed. I mentioned only one statement, but I would like to say something more. There are some other theorems, Lefschetz theorem for hypersurface in the torus. So there is a Lefschetz theorem, actually, which says that if you take a cohomology Hi of torus, and you take a restriction, map restriction to cohomology of hypersurface, then it will be isomorphism for I between 0 and d minus 2, and it will be injective for E I equals d minus 1. So that means it is not only one information. There is another information. So we have information that this statement, Lefschetz theorem, says that in small degrees the cohomology of hypersurface is the same as homology of a torus. And homology of a torus it's exterior algebra. But there is another statement, more general. It's not related to only to this situation. So the hypersurface is a fine variety. And a fine means also some vanishing conditions. So a fine cohomology of a fine varieties vanish more than, if you consider degree, more than half of dimension. So, and that means if you take, this will be 0 for I greater than or equal to d. So that means from all information that all interesting information actually for cohomology of hypersurface is a middle cohomology group. The middle cohomology group is just the group, this group, and you can compute dimension of this group, and so because you know all cohomology except this one, and also you know Euler number, your Euler number. So this information gives you, so you can make computation, and the dimension of this will be volume of a polytope plus I think d minus 1. If I'm not mistaken, yeah, d minus 1. So. Should I check? But I believe it's correct. So, but it's not only a fact what I need. So, as I said, we have a mapping. We have a mapping, a restriction mapping, and the restriction mapping it means there are some cohomology classes. So we have a restriction mapping from cohomology of a torus of degree to cohomology of a hypersurface. also the D minus. And in injective, that means there are some classes also in this group coming from a torus. Let us divide by these classes. So that means we are interested on those. And you know, this is because torus dimension D, it's degree D minus 1, so it's isomorphic to, it has dimension D. So we can define the primitive part of this cohomology just as a co-kernel of this map. And this primitive part will have dimension volume of the polytope minus 1. So we just delete D from. So actually this is the most interesting part. Well, and now I can explain you connection between this primitive part and what I explained previously, and to some rings that I defined. So the answer is the following. Yes.
Does the Lefschetz theorem depend on the regularity condition?
Yeah, yes, the Lefschetz theorem, of course, depends on the and you in classical Lefschetz theorem, yes. In projective case or in finite case, so it uses delta regularity, so you cannot avoid this. Yes. So now let me explain the relation between what I said. Now I'm forced to say something about Hodge structure, mixed Hodge structure. Well. There is actually, let me say that well, for any variety X, we are interested in cohomology of smooth variety, but it works for any variety. So we can consider cohomology or cohomology with compact supports. And for algebraic, if X algebraic variety, then the result of Deligne says that you can this cohomology have two filtration, which one is called Hodge filtration, and another is weight filtration. And both these filtration define two grading, so we can take grading pieces with respect to both filtration, and you come to some components, or homogeneous components, HPQ, which are called Hodge components, or in general Deligne Hodge components, and you can speak about Hodge component PQ in cohomology in any cohomology group of X or usual or with compact supports. So I don't want to speak much about how to define and how to and I think it's better would be just to look at one example where you can see these structures, and for me it will be more interesting to consider example d equals 2. So d equals 2 means that we have our variety will be curve in a torus of dimension 2, so affine curve, but complex curve. So you can take a closure of this torus. Usual way of taking closure, as explained, you take a toric compactification of a torus and then take a closure. And since you have a non-degeneracy condition, you automatically one can show that the closure under toric compactification will be smooth projective curve. Smooth projective. So smooth projective means that it's topologically it looks like in the usual way on the right, this curve. But our original curve differs from this compactification by points. So we should add some points. And if we look at the picture, so we have a polytope, two-dimensional polytope delta. So the points that we should add actually coming from one-dimensional sides of this polytope. So each side has some length, some lattice points, so the length of side is well defined, and each side define more. So if you go from toric curve to compactification, then each side gives you additional points. So the number of points. So if you look at the number of points, you have to add in order to get projective curve. So maybe, so if you take a projectivization and you delete open, so the cardinality of this point will be just number of points on the boundary of the polytope, on the intersection with the lattice. So you can see that it's. So this is a number. Well, you can. Of course, you can. Next question will be. Okay. So we know. Yes. Next question will be as the following. So we know that the cohomology of the projective curve, they can be described very easily. So projective curve has cohomology rank 1 in degree 0. It has rank 2g in degree 1, and it again rank 1 in degree 2. So we have such Betti numbers. So that means, well, the Euler number of this compact will be just 2 minus g. But if we go, but what our starting object was not compact curve, but was affine curve. So now we have to delete some points. And what happens with cohomology? So it turns out that if we delete only one point, we can kill the top cohomology group. So it doesn't influence on fundamental group of a curve. So if you have a projective curve, so we take this projective curve, we take away only one point from this curve. It doesn't influence on the fundamental group. But if we take more than 1 point, then we have additional non-trivial cycles one cycle that you can contract.
It does affect the fundamental group. It doesn't affect the homology.
Sorry, homology. Yeah. So it doesn't affect homology. Yeah. Sorry. Yeah. Sorry. Means factor fundamental group, abelian part. So homology. So that means so you can show that for this curve you always have degree 2 cohomology is 0, and degree 1 will be more complicated. So the dimension of this will be of affine curve will be a dimension of compactified curve plus plus the number of points we added minus 1. So that means so we have the number of points in the boundary. It's not the boundary, the polytope, but we delete from this point minus 1, so one less. And of course, H0 dimension of 0 remains the same. It's the same as 1. So now what I want to say, I can write down I can compute dimension of this cohomology in 2 ways. One way, as I mentioned at the beginning, I know that the not at the beginning, but I mentioned that the dimension in general, dimension of this cohomology group is volume of delta plus d minus 1. So it was on the in our situation. So for d equals 2, we have a dimension of cohomology of this affine curve is volume delta plus 1. On the other hand, you can compute cohomology by the formula that I wrote just now. Here's the formula. You take cohomology of compactification. It will be 2g, and you add number of lattice points on the boundary of the polytope, and again here minus 1. So the only interesting fact that I didn't mention in this, I explained how to compute dimension of cohomology, but there are some interesting pieces in cohomology, namely this half of the dimension genius can be computed. It's another result of Khovansky. It's number of interior lattice points, so you take just number of interior lattice points in delta. So if you substitute this in this formula, what you will get a relation between a number of lattice points on the boundary and lattice points on the interior and the volume of the lattice polytope in dimension 2, and it's a well-known relation which is called Pick theorem. So there is so you get some interesting combination. This is a situation that you will get. For curves. But let me explain more explicitly how the cohomology group looks like. As I said, there are some Hodge pieces. And therefore, we can write down cohomology. So we consider cohomology of a curve. And we have pieces. There are some pieces which coming, and here we have P, and here we have XQ. So the pieces of cohomology looks like as follows. So here there are two pieces coming from weight. So weight will be just here, and Hodge filtration is coming just. It's up to maybe just horizontal. The graded piece of Hodge filtrations are horizontal, and weight filtration just parallel to. Sorry. This is weight, and here's Hodge. So we have the following. So for the Hodge and weight filtration, we have a non-trivial component of H1, H1001, but there is some other component in cohomology, non-trivial H11. So the sum 1 is not 1, but still it appears, and the number and the dimension will be just the number of points in the boundary of the polytope. Again, boundary, -1. So, and here it will be 0. So this is a structure that one has for curves. Because we have duality for cohomology and cohomology with compact supports, we can write down again the table for cohomology with constant support, and it will be somehow a reflection along this diagonal. So there will be G here 0, and here will be number of lattice points in the boundary polytope -1. So here we have non-trivial part H00, H10, H01, and H11 will be 0. So they will be opposite. So from duality we have this opposite connection. So this is the structure that we get for the cohomology, and let us look at what I would like to suggest. Let us look at filtration. That means on this horizontal dimension. So with some dimension in any horizontal line. So here will be at least one element can be recognized very easily. Yes. Oh, sorry. Yes. Sorry. So we have. I would like to take summation. Let me explain what. I take another piece of paper. I would like to take so for cohomology, usual cohomology group of this affine curve. I take sums. Let me see. So yes. So I take some. I take H10 plus H11. This is one will be one dimension. So it will be number of lattice points in the polytope plus number of lattice points number of lattice points in the boundary of the polytope, or -1. So if you compute it, it will be a number of lattice points actually in the polytope, -1. But this is closely related to the dimension of homogeneous component of a Jacobian ring S1, because actually it's not exactly the same, because dimension of the homogeneous component can be computed its number of lattice points in the polytope minus d minus 1, so because we factorized by regular sequence. In our case, d is 2. You will have here you will have here you will have -1. So the difference is 2 is exactly the dimension of cohomology, the rank of the lattice M, which is cohomology of a torus. So that means if you delete from this number 2, so it's just dimension of a torus, or cohomology, one-dimensional cohomology of a torus, you exactly get this number. But if you take another cohomology, just H00 plus H01, so this is 0, we know, and this is number of interior points of the polytope. This will be exactly the dimension of second homogeneous component. So that means general result, which I want to say, looks as follows: for any polytope delta in dimension d, you have isomorphism between the graded features of Hodge filtration. So we have a Hodge filtration on a primitive part. So we take a primitive part of cohomology of hypersurface in degree d minus 1. We take a graded with Hodge filtration, and this is isomorphic to ring, but not the whole rings, only consisting of non-negative, so sum of non-negative degrees. So there is a 0 degree component of this ring, which is one-dimensional, but we drop this component. We consider maximal ideal, so it's the maximal homogeneous ideal in this ring. So there is such an isomorphism. So there's a correct relation. And at the same time, you can also write down the dual statement. So if you take a graded, also for primitive, but cohomology with compact supports, so d minus 1, again, but with compact support, you get isomorphism with homogeneous components of this module, except the last one. That means you summate from I until d, but you drop d plus 1. D plus 1 is one-dimensional, and it doesn't appear here. So this is a relation between commutative algebra rings that you obtain by factorizing by regular through a regular sequence, and cohomology, or interesting part of cohomology of hypersurface. So in my notes I have more examples, but what I would like now to say, yes. So there are some, as you see, there are some. There is a twisted version of this relation and construction. But I have only 10 minutes. I think it's too little time. Let me look what I probably... Oh, I forgot to say a very important statement, just for the connection to other talks. So maybe some example. I can also show some examples, but I think already dimension 2 example already had good good illustration for how you can also try to consider polytopes of dimension 3, but a general statement is the following. So if you so the cohomology of a hypersurface somehow, or cohomology with complex support, they are combined. They are not exactly equal, but they combine from two types of cohomology. So they are combined from cohomology of torus. So we take cohomology of a torus, dimension torus, and this is just exterior algebra of the lattice M, so canonical isomorphism. And there is another ingredient which influences on cohomology. This is exactly complex, Kazul complex that I already explained in my first lecture. So there is a Kazul complex of elements F1, F1 on elements in this graded ring. So this is another component. And actually, the first is and the whole cohomology is combined. So you can write down some sequence of complexes in the form. And this to the fact that cohomology of hypersurface combined from these two parts actually can be seen in the expression of zeta function and the composition in two parts: zeta function of a torus and zeta function of exponential sum. So, so the second part is responsible for exponential for computation of exponential sums. And actually, the method of Dwork looks as follows: we take some completion, or maybe not so easy. We make completion of this Kazul complex, and we compute. We have an action of Frobenius, and on Frobenius X on each component of this Kazul complex, but it acts as a Fredholm operator. But there is alternating sum of traces is well defined. So and we get what physicists called super trace, and we can so the whole machinery is actually related to this Kazul complex and any some version of this Kazul complex. And the other stuff is not so interesting. Well, they're trivial. Well, I have still 10 minutes left. Maybe I should. I have time to speak about twisted version. 5 minutes.
Is there any simple description of the Hodge member HGQ?
It's possible combinatorially write down a formula from any form of for Hodge numbers also contains two ingredients: combinatorics of the polytope, combinatorics of the phase relation. So we have a partially ordered set of phases. This and second ingredient, counting lattice points in phases or interior points in phases. So there are formulas, but they are not so they're complicated, unfortunately. So if you want to, it's possible to write down, but not so easy to work with this formula. So for some verification of toric mirror duality, I wrote a paper with Lev Borisov, and we computed actually in non-explicit way generating function for this Hodge numbers, because we wanted to check prediction of mirror duality for Calabi-Yau complete intersection toric varieties, and it was verified, but there was no explicit way of writing H coefficient. So we the function parameter. So the generating function for Hodge numbers has two variables, not one or two variables. We can work maybe better with functions, generating function, without knowing explicitly what this function, what coefficient of this function are, than to work with each coefficient in particular. So this is a problem. I don't know.
What can you say about this two-variable generating function?
Sorry.
What can you say about this two-variable generating function? It's hard to remember. Two-variable generating function.
Two-variable generating function. No, it takes time because. Well, if you need, for some application, just a formula for Hodge number of low-dimensional varieties like surfaces and also threefolds, the paper of Daniel Hansky, there is explicit formula for these cases. But if you want to do in arbitrary dimension, then there's some special function that invariance of partially ordered set. The combinatorics. Combinatorics not. I'm not prepared to write down this function. They're complicated. Twisted version. I have no time. But maybe you have questions. It's written in the notes, but maybe.
Question?
So should I tell about? The twisted version of all this appears in the following situation. We can assume we can change the lattice. So let me explain. We have a polytope, and we have and it has vertices in lattice. M. So we have also here lattice, but we can change the lattice in the sense that we can take a larger lattice, which is also still rational lattice. So we make an extension of the lattice. Of course, if you do such a thing, we can consider polynomial that we have this polynomial that we have a summation over lattice points. We can consider each lattice point as a lattice point in the am x to the power m. We can take as a lattice point in a bigger lattice. And there is a relation between two hypersurfaces. We will get actually a tail covering, Galois covering of one hypersurface from another hypersurface. So the hypersurface corresponding to second lattice will be covering or the hypersurface corresponding to original one. And the degree of this covering will be exactly index of this lattice. So if you have such a covering, you can split a finite abelian group, this Galois group, X on the covering, and it's X on cohomology. It's on cohomology and split cohomology in pieces corresponding to characters. So we have so many characters as order of that group, and we can look at homogeneous component with respect to character. And this will be twisted version. So we get again all the characteristic of this homogeneous component will be again volume of the polytope and etc. And there are some version of the polynomial genetic function that compute this homogeneous components. So this is a twisted version. But it appeared already, the computation for such a situation appeared already for quintic, for computation there was also a finite group if you construct a mirror of quintic. So it's related to. But now I think.